Bees. Doing this now. Okay, this will only record my screen. It won't record you guys, so I don't think you have to worry about that. So here we've got 18 letters. Now, if I'm writing this out using the fundamental counting principle, this is going to be 18 little spaces, and then I'm just going to write 18, 17, 16, 15, and so on. It's going to be kind of a pain. So instead, all I have to do is 18 factorial. And I want you to try and plug that into your calculator and take a look at the answer, see if you can make sense of it. Yeah, a very big number. So right away, your calculator is jumping right into scientific notation. And so I'm just going to go to 3 significant digits, which in this case doesn't really make much sense, but because it's so big, we get that huge, huge number. And this is the number of ways that we could arrange all of these letters. Okay, so factorial notation is kind of a neat way to shorten this, and at least to write it down and to calculate it, because it would have been a pain to write in 18, 17, 16 into our calculator. This way it lets us punch it in really quick. Now there's one really important thing that we have to accept, and that's that 0 factorial is a weird one. 0 factorial is 1. Now, we're gonna see kind of some reasons why we can think of that later, but for now I just want you to accept it. It sort of reminds me back in junior high when you were told that x to the 0 equals 1, and we just had to kind of accept it and say, okay, well, that's the case. Later on, as our understanding grew, we could see that that's a legitimate thing from a pattern, but for now, I just need you to accept that 0 factorial equals 1. Okay, so here's a couple things that we can do with this. 5 factorial is something I want you to think about. And I can write this in a whole bunch of different ways. Of course, I could just plug it into my calculator and find out that it's 120. 5 factorial is 120. Or, you know what, I could start to play around with this. I could say that instead of writing this as 5 factorial, I could write it in this familiar way. Okay, that's legitimate, that's equivalent. And I can start to get a little crazy if I want. I could say 5 times 4 factorial. Because you can see right in here, this part is really just 4 factorial, and so I could write it like that. Now, typically we don't put this times sign there. I'm just going to start to use a dot, 5 times 4 factorial, but they're equivalent. And then if I wanted to, I could do something kind of even different. I could write 5 factorial as 20 times 3 factorial. Now, you might, at first glance, maybe, okay, how did you get 20? Well, I just chose the first 2 there and said, okay, 5 times 4 is 20, and then all that's left is this 3 factorial, and so there I've got the 5 times 4, and there's the 3 times 2 times 1. There's the 3 factorial. So there's lots of different ways I could write this, but there it is. So here's a way to summarize that. 11 factorial is the same as writing 11 times 10 factorial. 6 factorial is the same as writing 6 times 5 times 4 times 3 factorial. Okay? Or we could write that as 120 times 3 factorial. Okay, so kind of a neat way that we get to think about this pattern and this product, and you'll see why this is useful by the time we get down here to the bottom. So express as a quotient of factorials. How am I going to write this guy as a factorial? Well, I'm recognizing that 6 times 5 times 4 kind of looks like the beginning of this whole thing, But because the 3 and the 2 and the 1 are missing, what I'm going to do is I'm going to build a little denominator that's going to let each one of these things cancel. And so I'm going to think of this as this. 6 factorial divided by 3 factorial. Okay, now for this next one, 13, I see this decreasing product and it kind of stops at 10. So what I'm going to imagine is that this is 13 factorial divided by 9 factorial. Cool, hey? So a neat way of writing even these segments or these partial factorials. All right, let's get generic here. Let's get to a general form. So now let's try something that doesn't have a prescribed number. This is going to be n factorial, which is the same as n times n minus 1 factorial. Similar pattern to this one right here. We've got 11 times 10 factorial. Now we've just got n times 1 less than that factorial. Okay, so I'm going to throw an equal sign in here. Here we have n plus 2 factorial, and I'm going to try to write this out a little bit. I'm noticing that there's an n factorial hanging out at the end of this thing. So I'm going to start with the biggest one, n plus 2, and then I'm going to go n plus 1, that's 1 less than n plus 2. And then, now I'd be at n. So I guess I could just go with that then. Let's move this over here. Done. Okay, so that's a way of writing that. It's kind of neat. I'm going to pause for a second here and just see if there's any questions. If you have a question, just flip on your mic and ask it. Not in this lesson. That'll be something for you to explore. And I'm going to say not in high school, but people have explored this idea. Can fractions have factorials? Can numbers other than integers or than positive integers or natural numbers have factorials? That's something for you to play around with. Okay. In our context, no, not at all. Okay, good question. So I'm going to keep on going here. Now we've got started to have this stuff in some neat expressions. So here's n plus 2 factorial divided by n factorial. And what my brain does as I look at this is I want to make this look simpler. So what I'm doing is I'm looking for which one is bigger. Is the numerator bigger or is the denominator bigger? And if you don't see that right off the bat, that it's the numerator that's bigger, try throwing in a number and say, oh, that's 12 factorial and 10 factorial. Yeah, I can see that the numerator here is the bigger of the two. Now, my brain wants that to happen first because then what I'm going to do is I'm going to start to expand that one like this. And once I get to the one that is in the denominator, I'm going to stop and I'm going to put a factorial by it. And then now we're going to start to simplify because n factorial divided by n factorial is just 1. Those are going to cancel because they form a 1. And so this is just n plus 2 times n plus 1. Okay, so kind of a neat thing that we can do now that we've got this new notation. Here's the next one. Yeah, go ahead, Zohab. Well, that's a great question. So let me go 5 factorial divided by 3 factorial. Instead of n plus 2, I've got 3 plus 2. And if I expand those, 5 times 4 times 3 times 2 times 1, and if I expand this, you can see that all of this stuff cancels here. And this is what I'm left with. So the factorial just represents that we have a repeated product decreasing down to 1. And so I'm going to say that, yes, the factorials cancel. But it's not really the factorials that are canceling. It's that factorial represents this whole product chain. And so that's what's canceling. Okay, good question. Okay, so I'm going to move on to the next one. I need you to think, which one of these is bigger? Is n minus 2 bigger, or is n minus 1 bigger? And if you're having trouble with that, of course, you're just going to throw a number in there. And you're going to see that this one is the bigger one. And so that bigger one is the one that I'm going to start to expand. So I'm going to write n minus 1, and then I'm going to get a little bit less than that. Oh, n minus 2. And there it is. That's the one that I'm going to put the factorial by. I'm not going to keep on writing this chain out. I'm just going to stop there because I've seen the one that I'm going to cancel with. Okay? And so now I'm going to cancel, and by cancel, I mean form a 1 because those are identical. And so I've got 1 over n minus 1 as my answer. Okay? Okay. So let's look at this next one. This next one's kind of different than the first two. N factorial is the only factorial. The other one's not. But you can see that this in the denominator is kind of the beginnings of that factorial. So what I'm going to do is I'm just going to start expanding the factorial. And then I'm going to stop there and put the factorial by that thing. Now, that factorial represents that I could continue this on and on and on all the way down to 1. But in this case, my goal is to simplify. So I'm going to stop there, and I'm going to let these things that are common cancel. And so this is just n minus 2 factorial. Love this stuff. I don't know why, but it just feels like it's a new rule that looks fun, but it kind of makes sense in all of the rules that we've had before. And it lets us make some progress in how we can work with these things. So here's the last one that I'm going to look at. And this is different. Here we're going to actually think of this as an equation, and we're going to solve it. In other words, we're going to figure out what n value makes this true. And my way of approaching this is I'm going to try to simplify this. So I'm looking at the top of the left side as the numerator being bigger. So that's the one I'm going to expand. N times n minus 1 times n minus 2. And I'm going to stop my expansion right there because that's the same thing that's in the denominator. So n minus 2 factorial is the thing in the denominator. And that's equal to 42. And then I'm going to cancel. And by cancel, I mean form a 1. And so now this is just n times n minus 1 is equal to 42. And then I'm going to expand this using my distributive property. So n squared minus n equals 42. And then I'll subtract 42 from both sides. And there's a quadratic equal to 0, and I'm going to solve it by factoring to find out what my roots are. So I'm thinking what multiplies to be 42, negative 42, and adds to be negative 1. So I'm thinking about 7 and 6, and I'll put the negative with the 7 and the positive with the 6 to make sure that the product is negative and that the sum is also negative. And so that means that I've got two answers to this, either n equals 7 or n equals negative 6. One of these is extraneous because we're only using natural numbers for this. We're only using positive integers for this. So this is the only solution. And you could try it out. You could plug it in, throw that expression into your calculator using 7. Here's maybe my check. 7 factorial divided by 7 minus 2 factorial. Well, that's simply 7 factorial divided by 5 factorial. And I'm going to expand the top. There's the cancellation. And there's 7 times 6. There's 42. The left side equals the right side. This is the solution. Okay? I love it. That's the end of this little bit that I wanted to do with you. So I'm going to stop my recording.